All right. Welcome to Math317 Operations Research. This is probably around day 29, day 30. What we're going to do today is we're going to do tomography, and we're going to do additional applications of linear programming. So the first exercise is called dead presence tomography. I'm curious as to see how well you can do in terms of naming who is on the different monetary units. Penny, Lincoln, nickel, Jefferson, dime, no, not Eisenhower, FDR, quarter, Washington, half dollar, Kennedy, dollar, depends. Oh, if it's the coin, there's a lot of different people who are on the coin. Susan B, Sacagawea, right?
Any president who's dead?
Any president who's dead. $2. Jefferson. $3. Yeah, exactly. So if anybody has a $3 bill, I get to break it to you. $5.
Abe Lincoln.
Abe Lincoln. 10. 20. Jackson.
Oops.
50. Grant. 100. Ben. And then can anybody name anything above the?
Didn't they discontinue?
James Madison was 5,000.
James Madison was 5,000. Robert Cleveland was 1,000. I think Salmon P. Chase was on one at one point. When he was Lincoln's Secretary of War, no, Secretary of Treasury, he was interested in running against Lincoln in 1864, and he actually put himself on the nation's currency, which was, I think, a brilliant idea. So what we're doing here is we're going to start off with a two-dimensional problem. So just so the people who are, so here is, a view of the first page. So if you look at this, the objects have different sizes. So we have pennies, nickels, dimes, and quarters. So if you go by size, we have penny, nickel, dime, quarter. Which is smallest, which is largest? So dime, and then
Penny.
and then
Nickel.
what was it, LE? Yeah, there's and then quarter. I think the dime and the penny are fairly close. Yes.
Do we know why there's a difference in size?
I think the way things are would be more amazing if things were the same size and it was still. I think it's also make it easy to just quickly look and see what you have. So then when things are different sizes, you don't confuse them. Although a lot of times dimes look like a penny when they get extremely dirty. So the way this works, and so for the first one, we have a 3x3 grid. And we have some coins that are placed down. And you are given information about what happens when you shine light in a direction. So we'll assume all the coins in a square are perfectly centered. There's at most one coin in each square. And when you shine it like this, the shadow is the shadow of a dime. When you shine it like this, the shadow is that of a nickel. And when you shine it like this, there's nothing there. When you come down like this, you see the shadow of a nickel, shadow of nothing, and shadow of a dime. So this is all the information you have. And the goal is, what can you say about the internal structure? So can anybody give me a real-world problem that's probably similar to this? Why might we care about this? Yes?
Is this a game?
It can be a game.
Could you elaborate a little more on?
So if you wanted to make it a game, one person puts down coins and tells the other person what you have as you shine, and then the other person has to try to reproduce it. So if you want to make it a game like that.
Body imaging scans?
Yeah, body imaging scans. How do we image people now? What do we use? I'm sorry? Okay, what is MRI? Rays. What kind of rays? Radio waves. Good or bad for the body? Not good, right? So if it's not good, why would we do this to people?
Because the benefit's greater than the cost.
So the benefit is greater than the cost if you do things in moderation. Right? So the question is always, how valuable is the information and what is the cost to get it? The more ways we shoot, the better sense we have of what's going on. You shoot so much, we now know exactly where all your diseases are. Oh, you're dead, sorry. Right? So you should think of it as every piece of information, there is a cost. So what do you think we might care about in an operations research class? Yes?
Runtime/efficiency/time it takes.
Okay, so what is runtime? Is how long is it going to take us to get the information? Has anybody actually been, I've been in a CAT scan. Has anybody been in a CAT scan? Okay. Is this something you would like to do again? No. Okay, so the shorter time it is, the better. How many of you have ever had scans of your teeth? Where they put those, wonderfully nice squares and have you bite down on them and they shine the laser after they get out of the room? Right? We'll be right back, right? Now, why are they getting out of the room?
They're exposed every day.
Yeah, they're exposed every day. You're just coming in here every now and then, maybe once every 6 months, once a year. So for you, it's not a big deal. But if they're doing it multiple times a week, even if it's not that big of a deal, cumulative, it could be bad. So they will go to another room. It's not fun when you're biting down on those things. So the question is, how long does it take to actually get the information? If it takes too long, especially when you have a little kid, the likelihood of the kid not holding still increases the longer you run. So the need for efficiency is huge for something like this. Okay, so one was efficiency. What else? Why else might we care about this in operations research class?
Probably be solved faster.
There's a problem to be solved?
Yeah, well, you could probably solve this with integer.
Yes, we could probably solve this with integer programming, and in fact, we will try to do that later today. Integer programming may not be the best way to solve it, but it should hopefully be one way to solve it. But what else might we care about when we're doing this? We care about efficiency. It's related to something I mentioned a few times.
Cost.
Cost. So what is the cost? How do we factor the cost?
How much tissue you're destroying, I guess.
Okay, so there's two ways of cost. So you're actually concerned about the patient. I was actually concerned about the bottom line for the company. How much is each image costing me to make? So both are valid points, and both should be considered, right? So every time you're doing this, you're causing some damage. And that at some point, you're not getting enough information to justify. So how many pieces of information do you need? Which pieces of information do you need? Are there some shots that are better than others? Years ago, my mentor from the physics department at Yale was suffering from cancer and he was getting radiation treatment. And his doctor was one of his former students. And on his last treatment session, the machine broke. And the student was just mortified that the machine broke with his advisor there. And he promised him that he will pull strings and make sure that when the machine is fixed, I will get you on the list as fast as possible, but I don't know how long it's going to take us to get this fixed. And then my advisor said, well, actually, I am a nuclear physicist. I heard something. Can I take a look at it? And he said it was the only time in his personal life where it was useful to be a nuclear physicist. He was able to get the machine running in 15 minutes. And so over here, I will give you a few moments, work by yourself or work with the person next to you and figure out what can you deduce from this. Yes?
Do we know anything more than just exactly?
This is what you know. So do the first problem and see what you can get.
Well, what is the problem? Like, what do we get?
What can you deduce about what's in here from what I'm telling you here? I'm telling you, if you shine a light, you see a dime.
So, and it can be.
I'm not telling you anything more. That's all I'm telling you. I'm giving you very little information. I will start working on the next thing.
In this kind of thing, this is almost similar to the Battleship.
Yes.
Is it ever like a storage efficiency to store like the row or column sums and then calculate that rather than just sending the whole like end by end of like the actual
Right.
information?
So that's a different question in terms of efficiency of storage.
Uh-huh.
That for a lot of things, it is much easier to save smaller amounts than we produce. Like that's why we send Fourier coefficients or Taylor series coefficients rather than the whole function. Or all the squares. I'm not telling you anything else. I'm deliberately not telling you things.
Make it easier on yourself.
So,
For some of them, there's no way there would be coins, because otherwise it would be a shadow from a coin.
right. I'm deliberately not telling you things. I'm giving you the freedom to choose how you want to tackle the problem. And if you make the wrong decision, a cute little puppy or kid will die. Just no pressure. Puppies are fun. Okay. Yeah, and if you finish the first one, you're welcome to look at the second.
I was thinking that.
And then the cell phone policy is on hold today. Kayla's home's partially sick. All right. Hello? I'm glad I said that right before the phone rang. I did write it on the board though. All right. Does anybody want to say anything that they can deduce from this problem? And in an ideal world, I would have multicolored chalk, but the multicolored chalk doesn't erase well.
There are no coins in the middle column or the bottom row.
Right, so having a nothing here is very useful. We know nothing, 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 and nothing, nothing. So if each square is worth the same as every other, you've at least broken 50%.
You can't have a nickel in the top left or top right, because otherwise it would show you'd basically blot out the dime.
Okay, so there's no nickel here?
Yeah. Or there's no nickel on the two right squares either.
Over here, no nickel?
Correct.
And no nickel here?
Yep.
We also know something else. Yes.
There's no quarters.
Right.
Okay.
And
It's a little hard to
we also know something else. Yes.
We know there has to be a nickel in that last empty square, because we need a nickel in the row and the column, and we can't have nickels in the other squares.
Right. So we know there has to be a nickel here. So we know there must be nickel because if we know there can't be a nickel here, because if there was a nickel here, we wouldn't be able to see the dime. Right? So if there was a nickel here, as we shine the light in this direction, if there was a nickel here, that would block the dime. The nickel is bigger than the dime. You look confused in the back.
Yeah, you didn't give us any rules, so I'm just running through potential rules in my head. Can they add up, like two nickels add up?
No, it's just, we're shining light like this.
I don't necessarily know what that means.
So when we shine it like this, we're getting an image of what comes through. And as we shine the light, it comes back and tells us that there's a circle the size of a nickel. It fills up that much. So for instance, if I had a dime followed by a nickel, and I shined the light like this, if you look below, you would see the shadow of a nickel. So think of it as, you have a light coming down like this. If I have a dime over here and then a nickel underneath, and I look down on the plane over here, the shadow of the nickel fills up the shadow of the dime. The shadow of the dime lies on the nickel, and then the nickel shadow fills that up. So we can't have a nickel here, because if we had a nickel here, it would block the dime. Could we have, so we can't have a nickel here, so we could only have a dime or a penny. We know we have to have a nickel here because we see a nickel below. Yes, what else do we know?
I was gonna say you couldn't have a penny there because you shine a light to the right. If you had a penny, it would block out the dime and you couldn't see a dime.
Okay, so we can't have a penny here?
Yeah.
Okay, so
Or
no
I guess
penny.
in the top right.
No penny.
Or the last one.
Or the last one. So in fact, we now know there's no quarter and there's no penny. So I will remove the penny here, because there's no need in noting that, because I can just write there's no penny anywhere. What else must we know?
There is a dime in the top right corner, or there is a dime in both of the other two spots.
Right.
Or
So we,
all three.
or all three.
Well, yeah, that's why I said
Yes.
inclusive
And so
or.
there's inclusive or. Right. So,
I guess you could say you need to have at least one dime in the top row and at least one dime in the right column, and however you want to do that.
okay, so the question is, how do we want to phrase all this? So you said, let's label these squares 1, 2, 3, 4, 5, 6. So what was your statement?
There's a
Dime in
3 or dime in 1 and dime in 6. And the 1 and dime in 6 is in parentheses.
So if we have a dime in 3, then when we shine it like this, we would see a dime. And we know there's no nickel there, so it could be a dime or not a dime. When we shine it over here, we'd still see the nickel. When we shine it down, we're fine. When we shine it down, we would see a dime. So if we put a dime in 3, we're okay. If we put a dime in 1 and 6, then the nickel here is going to block the dime. That's good. When we come over here, if there's a dime in 3, we already said that there was no nickel in 3, then it could be a dime or not. So is this a unique solution? No, there is not a unique solution to this. What's the problem with not having a unique solution? So think of these as cancer cells, yeah.
Hard to verify.
What do you mean by hard to verify?
We think about it as a puzzle, it's hard to verify it, like if someone gets the correct solution.
Well, there could be, so there's multiple solutions. So what's the problem with having multiple solutions?
If you're cancer cells and you need to use your gamma lasers to zap the cancer cells, you're now killing 3 times as many cells.
So one possibility is, let's just shoot everything and have God sort it out later. That's one philosophy. Yes?
So maybe to build off Will's point, from the business side, bottom line, maybe you're using too much money per patient if you don't have certainty, and maybe on the patient side, you could potentially kill them much more quickly if you can't be certain about how much treatment you need.
Right. So what should we do?
Have some cost function to optimize by.
Okay, but so what would we do? So one possibility is we could maybe gamble, and we could look at what configurations are possible. So we need the pairs 1, 3, 6. What are the possibilities for 1, 3, 6? Let's see how many different solutions we have.
I think that's 5.
Okay. What are they?
3 alone.
Okay, 3 alone. So basically blank, dime, blank. So if we do that, we're fine.
And then any set of 2 will work.
And so any set of 2 works. So if we do dime, dime, blank, that's okay.
Or blank and dime.
Okay. So blank, let's do dime, blank, dime, blank, dime, dime, and there's one more. Dime, dime, dime. All right, so we have at least 5 solutions. I think that's probably it. If not, you can. So what would you gamble? Would you irradiate everything? Would you irradiate maybe 2 out of 3? Would you try to get more information?
If you're doing 1, you would irradiate 3. If you could get more information, if you could shine a diagonal laser.
Right, so one possibility is maybe it would be good to now look at some things diagonally. And the question is, what's the best way to get more information? And there's going to be cost. You would need to look at what is the cost of gathering the additional information versus the cost of just irradiating. Hopefully the cost is not too much. Yes?
In this example, we might not necessarily be able to gather more information, right? But are you saying that
Well, right, well, for this one, we could shine lights diagonally, and that would give us more information. But there will be times when you can't get information that some things are hidden. You're not going to be allowed to just open somebody up, rip out some parts, look in, and just put things back. And so it becomes a really interesting question as to how can you get the information without destroying the object you care about. But what do we know with certainty for this? We know a lot with certainty.
I mean, we know exactly what's in the other 6.
Right, we know exactly what's in the other 6. So we know 5 squares are free, and we know there's a nickel here. Now, which do you think is the most dangerous coin for this problem? The nickel. That's probably the largest of all the cancer cells. So, fortunately, in this configuration, we know that all the other ones are at least no more than a dime. And so maybe the ones that are no more than a dime could be in the situation where, you know what, we can afford to just let it go for a while. And then this is the only one we really need to treat, and we're lucky it's on the boundary. And we can just get to that without getting through healthy cells. So there's a lot of other problems here. If you want to look at them at home, you're welcome to it. If this was a class that still had a large amount of homework, I would assign a bunch of them. But it's the end of the semester. I want to give you a time to really work on projects. But it's an interesting question about how much information can you glean from these? How many different configurations can you have? Which cells do you know for certainty what the values are? And then the other question is, if you want to turn this into a game like Sudoku, would you consider this as a good board? So why would this not be a good board? It's not unique. So, you can clearly give a Sudoku board where it's not unique. And there's a rule that basically whenever you have a problem in a magazine and a newspaper for Sudoku, there should be a unique solution that you can get to without guessing. Now, you might have to try something and backtrack for a little bit, but there should be a way to just keep plugging and plugging and plugging and not just complete brute force. Right? Any questions about this? So building on our success here, what do you think we do next? So what should we do now building on this success? What problem should we look at next? Yes?
A bigger board.
So one possibility is the bigger board. There's often more than one way to generalize. What's going to be the difficulty with a bigger board? Yes?
Well, on a bigger board, you might have quarters and pennies, and maybe.
Right, so in a bigger board, we're probably more likely, depending on how sick the person is, to have more coins. What else?
I mean, in this case, where the board is growing by n squared and our sides are growing by n, so we're losing information every time we grow the board.
Good, so as the board gets larger and larger and larger, we're getting less and less information relative to how many cells there are. And what's the danger that could happen on a large board?
It's going to hide a bunch more.
Yeah, it becomes more and more likely that things are hidden that you won't be able to get to. So if we could actually irradiate from above, all we need to know is where things are now, and then we could just irradiate. So even if something was hidden, we could hopefully then still reach it. So we could absolutely look at larger boards. What else could we do? What else could we look at?
Go 3D.
We could go 3D. And building on our success in 3D, what could we do after that? Right. Now, in terms of doing something in the lab, in the real world, we're not going to do a 4-dimensional problem. But mathematically, if you want to think about, you have this high-dimensional structure, and you have slices, and you have some information about it, and you're trying to recover, then the idea is maybe we could look at a 4 or 5 or 6-dimensional object and just try to reproduce things. I was hearing a couple of other comments that I want to just briefly mention. Somebody said that this is very similar to something we did earlier in the semester, the Battleship Game. The difference with the Battleship Game is you find out exactly how many cells are on in a given row or column. Whereas here, you have a shadow. Yes?
What's the value of going into 5, 6, 7 dimensions and then trying to take that into the realm of healthcare? Are you going with this?
Well, I mean, it would not be a healthcare problem. It would be more, you have some multidimensional object, and you're trying to encode information and transmit it.
I guess I mean more generally in pure mathematics. When you go into 5, 6, 7th dimension, how is that necessarily useful when you go back to the dimensions of human beings?
Well, so for instance, if I want to send an image, I don't want to send the value of each pixel. That's extremely expensive. What I could do is imagine I have my red function, my green function, and my, is it blue? And blue. Do people know how images are transmitted? Let me just briefly say how images are transmitted. So, And actually, I can use this as an example of how to hide images. So you have a red, green, blue triple, and you want to send that. And typically, we take these each from 0 to 255. So the number of colors you have, I'm not sure why it keeps going down. The number of colors you have is 255 cubed choices. Right? We can't really distinguish that many different colors, yes?
I think you may have hidden it.
Oh, sorry.
No, the remote. I think you may have hidden it.
Oh, maybe. Thank you. So we have 256 cubed. Roughly, this is at least 200 cubed, which is 2, 4, 8, 1, 2, 3, 4, 5, 6. So there's more than 8 million possibilities. And if you do 2.5, you can see. So do you think you can see 8 million different shades? This is plenty of detail for anything we want to send. And so if you have a large image that you want to send in my photo, we have the red, the green, and the blue. And so one possibility is, for each little cell here, we have a value of red, green, and blue. And we send each one of those values. That's going to be extremely expensive. So one thing that's often done is maybe you look at the red function, the green function, and the blue function. And we've seen Taylor series expansions in one variable. And you write f of x as a sum of an x to the n. So this is a series expansion. And the hope is that for most functions, you don't need that many Taylor coefficients to capture what's going on. So if you look at, this is going three-dimensional now. Right. If you look at, say, f of x is cosine of x. Okay. If we try to write the Taylor series expansion for that, you get the Taylor series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so on and so on. And maybe we've normalized things so that minus pi less than equal to x is less than equal to pi. N factorial is approximately n to the n e to the minus n squared of 2 pi n. So n factorial is growing very rapidly. So once I take a couple of terms, it does a phenomenal job approximating cosine. And so if I want to send a plot of cosine, one possibility is I send a tremendous number of points. And each point will be an x coordinate and a y coordinate. And I could do this, and I could transmit all that information. But that's very expensive. Instead, I transmit 1, 0, minus a half, 0, 1/24, 0, 1 over 720. I'm sorry? Minus 1, thank you. So if I transmit those 7 values, I would then be able to construct a really good approximation to cosine. And it's very cheap. And the probability of you being able to detect visually the difference between that and the true cosine function is minimal. That's far better than doing 10,000 data points. So we'll probably talk about this again later in the semester. Rather than doing something in just 1 dimension, I can do something in 2 dimension. I could have my red function, and I could find what is the best approximation to that function. Instead of using the Taylor series with polynomials that are just 1 x squared x cubed, it's actually a lot better to use maybe sines and cosines or special function bases. And the idea is you only have to transmit a couple of values. And just by transmitting those few values, you can then send the image. And so one of the things we might want to do, you wanted like a higher dimensional problem, is I want to sniff out maybe what the coefficients are. And so I might have, yeah, this is a 7-dimensional problem here. What are the best 7 values for this? And by looking at slices and information, I might try to get things. As an aside, you can actually use this to do cryptography and to hide messages. So just briefly mention this is a fun application. I need a color, red, green, or blue.
Right.
Red? Blue, we'll do blue. So what we're going to do is we're only going to look now at the blue image. And for each pixel here, we can write it as, we've done a lot of things by doing things in different bases. And so we can write the color at the point ij as b ij0 times 1 plus b ij1 times 2 plus b ij3 times 2 squared plus dot plus b ij, going up to 256, yes?
Could you try turning the remote so that the color is facing the left?
Sure. Hopefully that will work. So we got 2, 4, 8, 16, 32, 64, 128, 256. We go all the way up to 8. So you give me any pixel value, and I can associate it to a triple bij0, bij1, bij8. Oh wait, no, we would go up to 7, sorry. Let's start with the 7. Okay? If I change just the last digit, is it going to change the color by that much? No. So here's, it's called steganography. Write a message. Write it in black ink on a white piece of paper. Pixelate that. And then change this last digit to match the image you're trying to secretly encode. And if your last digit has a black cell there, you put a 1. If it has a white cell, you put a 0. And what you can do is you can then hide a Word document, and you can bury it in the image. If you wanted to do something more involved than just burying an image, what you could do is you could just change the last maybe 1 or 2 digits of red, green, and blue. How many colors would that give you if you could change the last 2 digits? So if you change the last 2 digits of the red, the last 2 digits of the green, and the last 2 digits of the blue, how many colors would you have? I'm sorry?
I think 4 cubed.
4 cubed, and thank you for pronouncing it well, or 64. Is 64 colors enough to have a decent image? Yeah, I mean, it's not going to be as great as having 256 shades for each color, but 4 shades for each is going to give you the possibility of 64 different colors. That's already a decent Crayola set. This is not the dinky 8 colors, which is what you would get if you just changed the last digit. And in fact, when you look at your original image, sometimes you will actually have the correct value. And so you can actually bury images inside images. And then the real question is, can you detect if somebody has done something like this? Yes?
I'm not completely sure, but in cryptography, do we have functions, mappings?
We can.
And is that what this mapping would be? You take the last one and you switch
Right.
the value.
And so we would switch either the last value or the last 2 values, depending on how much information we want to embed, to match the image we want to hide.
And if someone wanted to crack this, they would have to come across that pattern.
Correct. And so if you know to check this, then it's very easy to check and see is there an image. You just strip out all but the last 2. So what you might want to do is you might want to have a function that changes these values based on maybe the indices as well, where only you know that, and then you would know how to interpret it.
You could also crack the last digit one with like Microsoft Paint. Do it carefully.
I'm sorry?
You can crack, if someone's done it poorly, you can crack it with Paint.
By poorly, you mean just changing the last digit? Yes. But so what you would want to do is if you're going to do this, you would actually want to have some kind of way to encode this. And so maybe you would know a secret formula. Maybe you multiply this value by, yes?
So do people use prime
I don't really want to go into primes because this is different than the primes in the RSA and stuff like this.
But generally, you just want to pick something that people don't know what the hell is.
You want to pick something which is easy to do if you know the back door and hard to do otherwise. And so over here, this is just a great way to encode an image without too much trouble. So we could do the two-dimensional version. We could also do the three-dimensional version. So, given that I play with Legos a lot, here's the cheap three-dimensional version. All right, so I have made a little board. I put a little green dot over here just so I have the orientation. And then what you can do is you can play the same game. So, I have a bunch of little pieces. And so I'll place a couple of the pieces down. And each piece can be either, say, bottom, middle, or top. And so depending on how I put them, so I don't know how viewable this will be, but so I've placed it now, I've got a couple of things over here. And let me see, I want one more, I think. And I want two more. Okay. Not two more, two more. Okay. So we can play the same game as before. Sure. Good. Okay. So what you do now is you get different slices. So I can shine the light from above and see what the shadow is. And when I do that for this one, you can see that there's nothing in any of these three. And there's something in the other ones here. So what we would do is we would play the same game as before. And so if we do the top, so when we would shine down on this one from the top, we would have something here. So do we want to use an X for something, or do we want to use an O? O. We would have something, 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 nothing, nothing, nothing. So which pieces of information are the most valuable from this? The nothings. We know there's nothing in those. Now we can look at what happens if we shine it from the front. So if we shine it from the front, there's nothing when we look at it this way. So that means there's going to be nothing, nothing, nothing. That's valuable. When we go it this way, there's nothing in the bottom. There's something in the middle, and there's something at the top.
Something at the top?
Oh, sorry, something at the top, yes. When we did this with teachers, we used X's, and so I'm just trying to do it. And when we do it this way, we see something in each one, because there's something at different levels. So we get a lot of information from the front. And then the last is from the right. So if we look at it from the right-hand side, when we go over here, it's going to be something, nothing, something. So something, nothing, something. And the next one, it's going to be nothing, something, something. And then the last one is going to be something, something, nothing. And so the question is, when you have information like this, is this enough to uniquely determine the configuration?
I
Yes.
think you, on the bottom left-hand corner of the front should be an O.
Let me check. So the bottom left corner. Oh, there is one in the back. Thank you. Yes. I did not see that because I was holding it. Thank you. So is this enough information? So I have the advantage of being able to look directly at it. Let's consider the thing that's in the exact center. So think of a Rubik's Cube, right? You have 26 pieces on the outside, and then you have the center that you can't reach. Can we tell what's going on in the center? Well, when I look down from the top, this one over here actually blocks it. When I come like this, if this was here or not, I would still see something because of this one over here. And when I come in from this side, I would still see one from this over here. So in a configuration like this, we might not have enough information to uniquely determine what the configuration is. And then you would ask, would you want to maybe be doing other kind of planes, slicing like that, and getting information? How would you set this up as the linear programming problem? You've got about 8 minutes left. Right. Hopefully linear programming can solve this. Yeah, this is one of the big tools we learned. What would our variables be? What would our objective function be?
So, since we have a 9, we have a 27, right? Different boxes. Each x sub I, j, k. 1 if something is there, 0 if something isn't. We know that the sum.
Okay, good. So these are going to be the binary variables. 1 if something is 0, 0 if nothing. Okay.
So we know which columns, rows, and whatever the third thing is. We know when they will sum to 0, and when they must sum to something greater than or equal to 1.
Good. So now we have the constraints from coming in. So let's say, so we have t is coming from the top. So we have, Tij is going to be our values coming from the top. And similarly we'll have front, and similarly we'll have right. So this is going to be 1 if an x, 0 if an O. And now, what's our constraint going to be for, say, T11?
So it's the sum of x11k for all k has to be greater than or equal to. Sorry, no, that's not right. Because if it's 0, you want it to be 0. But if it's
Okay, well, you just used a really nice word.
or,
No.
if.
So, if T11 equals 0, then the sum equals 0. So then it would be the sum of x11k equals 0. We can't have anything in that column. And then if T11 equals 1, then what?
It has to be greater than 0.
I say greater than equal to 1. And then we just keep putting in constraints like that. What should our objective function be?
Anything?
So this is where things get interesting. You have several choices. You could have the supersick objective function, where you want to maximize the number of infected cells. And this could give you a sense of what is the worst case for your patient. What's the maximum amount of infection they could have. You could do the best case objective function. What is the healthiest the patient could be given this? You would have some kind of range. You could also say, maybe I want certain cells, I really want to know about this value. Is there any way this cell could be healthy? And so you could put in an additional constraint, would this be a feasible solution if this cell had to be healthy? How happy are you about putting in if statements? Is it terrible to put in an if statement? If the problem was originally a real integer programming problem, it's really bad to put in if statements because you've converted from a real integer programming problem to an integer programming problem. So if you have a real programming problem where the variables are real, we can solve this using the simplex method. It's fast, it's efficient. As soon as you put in if statements, we have to introduce binary variables. And now we go to having a binary integer programming problem, which is equivalent to the traffic salesman, is equivalent to all these other hard problems from computer science that we just can't do. But given that we're already at an integer programming problem, it's not horrible to be putting in more ifs. There is a way to get rid of one of the ifs.
the options are 0 and 1, so you could do an else instead.
Okay, we haven't programmed else, but you could try to do it as an else. I claim we actually could replace this second condition with something that avoids the if. Yes.
You just said sum of x11k is greater than or equal to t11.
Yes, because if t11 equals 0, then we force the sum to be 0. So we can just replace this with just t11. We actually don't need the if statement. And then if t11 is 1, that will then force the sum to be at least 1. And so you can avoid the second if at least. That's worth doing. You know, that will cut down, you know, especially when you consider how many times we have to do this. And then the real question is just how many slices do you want to take? And where do you want to take the slices? What is the cost of taking the slice? And you know, as we said, there are two types of costs. There's the cost to the patient, and there's the cost to the company. Then you want to figure out maybe, you know, if things are different sizes, what kind of mistakes can you live with? Or maybe it should be the patient can live with. So sometimes it's not worth getting information if the amount is just negligible. But maybe you are worried that somebody could have some cells that could become a problem in the future, and if you can correct it early, it's tremendously valuable. That if you wait until things grow too far, the cost is minimal, it's not going to be that inconvenient. So there's a lot of tremendous trade-offs for this. And then when you're doing your imaging, it's a lot of interest now as to which way do they gather the data, and then how do the machines piece them back together. I'm not saying they do it with linear programming, I'm saying this is one of the things you can do. And one of the problems is that you are not always going to be able to recover uniquely what you want. And then you have to decide how do you want to deal with that. All right, so this is a good place to stop.